Okay, in the last class we are discussing this delay optimization. So, for that we consider what is called lifetime chart, which gives us the minimum number of this thing, I mean the maximum number of live variables at any stage, okay, because you need to provide that many registers, okay. Minimum number of live variables, okay, or say number of live variables at any stage, and you find the maximum of them, rather I am sorry, you find the maximum of them because that many registers are required to solve them, save them. So, that we discussed, and then we asked this question that who will give you the description of the lifetime of the variables, like each variable, if you consider a variable, say A, in which cycle it is born, which cycle it is dead, and so on and so forth, and what will be the period of the system, because this will be periodic, right, same phenomenon will occur again and again. So, for all these you really have to carry out what is called the lifetime analysis of the system, that is you have to really investigate what are the variables, in which cycles they get generated, in which cycles they get consumed, that is they become dead, for how many cycles they remain alive, that is they require to be stored in some delay registers, and what is the period of the system and all that. To explain that, we consider a very nice example from the book by Keshav Parhi, because it is very insightful. So, I repeat what we discussed last time briefly, that suppose we are given a problem that you have to transpose a matrix, okay, you have to transpose a matrix, like capital A is a 3 by 3 matrix, you have to transpose it. So, transposition as you see is given here, A, B, C, D, E, F, G, H, I, that is A, and transposition is A, D, G, B, E, H, C, F, I, this matrix. Okay. Now, suppose this matrix A is coming in cycle after cycle, new and new matrices are given to the system, system will read and then write a new matrix which is the transpose of the particular matrix that is read in that particular cycle. So, suppose in a particular cycle, say Lth cycle, the system reads this. So, what it does, it takes the whole of Lth input cycle, divides it into 9 parts, 9 sub cycles, that is 9 system cycles, okay, which is faster, because each input cycle is divided into 9 system cycles. Okay, so, system clock goes up by 9. In one of them, which is 9L plus 0, it reads, reader is positioned at this position, there is 1 comma 1 position of the matrix, it reads A. Writer also is simultaneously positioned in a matrix which is to be filled, it is currently it is empty, but in the 1 comma 1 location, and they are synchronized, they move together. So, in 9L plus 0, it reads the sample A. So, this 0 means T input 0 means 9L plus 0. It is not required to be conjugated because writer will write it in the same place 1 comma 1. So, no need to store it, that is why T output was 0, and in the difference between them is 0 cycle, that is why I need only 0 cycles to store them, that is I do not need any cycles. Okay. Let us go up to this. Then reader moves at 9L plus 1, moves to B, it reads B, writer also moves here at 1 comma 2 position, but then you see here it does not write D, it does not have to write B, it will write B only when it goes here, that is 9L plus 0, 9L plus 1, 9L plus 2, 9L plus 3. So, B will be written when the writer is in the cycle 9L plus 3. I am writing 3, the 9L is there, that I am dropping just for the sake of clarity. So, it is read in cycle 1, that is 9L plus 1 on the reader side, it is stored, it is consumed or it is used up in 9L plus 3. Okay. So, difference actually it is wrong, the difference between them is 2, not 3, 3 minus 1 is 2. Okay. Then reader moves further at 9L plus 2, it goes to C, but here writer also moves here, but it does not write C. When does it write C? When it is coming to this position. That means 9L plus 0, 9L plus 1, 9L plus 2, 9L plus 3, 9L plus 4, 9L plus 5, 9L plus 6. So, at 9L plus 6, writer is at this position, that is 3 comma 1 position, that is the time when it writes C. So, C is read in cycle 2, but written in cycle 6, 9L plus 6. So, difference is 4, all right. Then reader moves further, it goes to this position 2 comma 1 at 9L plus 3, 0, 1, 2, 3, 9L plus 3. but it has to write B in this position, where the writer was in which cycle? 9L plus 1. So, input is 3, output is 1, 9L plus 3, 9L plus 1. So, difference is negative. That is a problem, it becomes non-causal. Anyway, let us still carry on. Then reader moves further, it reads E in 9L plus 4. Writer also moves here at 9L plus 4. Here E is read and immediately written, no need to store. So, 4 and 4. So, I mean difference in cycle is 0. Then reader moves further at 9L plus 5, goes to read F, but F is required here at which cycle? 9L plus 0, 1, 2, 3, 4, 5, 6, 7. So, it is cycle 7. So, it has to be stored from 9L plus 5 to 9L plus 7. So, how many cycles? 2 cycles. Then it moves to G, this position 3, 1, it reads D, but G is to be written when the writer was in this position 1, 3. That is when the writer was in which cycle? 9L plus 0, 1, 2. So, that is why 9L plus 2, and that is written in 6. So, again negative 2 minus 6, which is minus 4. We further carry on in 9L plus 7, reader comes to this position H, it reads H, but H is to be written here at this position, which is 2, 3. So, that was at 9L plus 0, 1, 2, 3, 4, 5. So, 9L plus 5. So, here again there is a causality problem, read in cycle 7, but to be written in cycle 5. So, minus 2. And lastly, I, this is read by this reader at 9L plus 8 and also written in the same place. So, 9L plus 8. So, difference is 0. To take care of the causality problem, what we do now? We see the maximally negative value, minus 4. So, we say that let the reader start at 9L plus 0 and go ahead as it is, but let there be a delay, a latency, a delay in the writer. Writer should start writing at 9L plus 4. Okay, so, only at 9L plus 4, it will be in this position, in this empty matrix. Okay, which position? 1, 1. But reader will be at 1, 1 in cycle 9L plus 0. If that be, that means earlier output, earlier A was read in 9L plus 0, which is same now, but earlier A was written in 9L plus 0, now I have to add 4 to that. So, it becomes 4, alright, and the difference is now 4 cycles. This arrow and the subsequent, after the arrow whatever I write, there is a new difference. The new difference is 4 because this is delayed by 4. Then B, this fellow reader reads B at 1 as before, but writer will write B when writer is here. What is that cycle? Writer is here 9L plus 4, 5, 6. So, writer will have to write C, sorry, I mean, yeah, let us consider B. Let us consider B. So, at 9L plus 1, reader reads B, no problem, but writer will write it only when it is here. At what cycle then? Earlier it was at cycle 3, now it will be added by 4. So, 4 actually 9L plus 4, 9L plus 5, 9L plus 6, 9L plus 7. So, earlier it was 3, now 3 plus 4, 7. So, difference is 7 minus 3, sorry 7 minus 1, 6. Earlier difference was 2, so 2 plus 4 either way, so 6. Then reader goes to C in cycle 2, but writer will write C at this position, right. So, that is earlier C was written at 6, so 9L plus 0, now it will be written as 6 plus 4, 10, that is 9L plus 4, 5, 6, 7, 8, 9, 10. So, 10. So, read in cycle 2, but written in 10. So, difference is 8. So, it has to be stored in longer duration, okay, stored for longer duration. Earlier it was only for 4 cycle, now it is 8 cycle. Everybody is getting added by 4. Then D. D is read as before at cycle 3, that is 9L plus 3, but writer will write it at when the writer finds it in this position, that is 9L plus 5. Okay, 9L plus 4, 9L plus 5. So, D is 5, that is 1 plus 4, you can see that way also 5. So, cycle read in 3, written in 5, so difference is 2. Earlier difference was minus 2. Now, I have got rid of the minus 3. Then come to E. E was read in cycle 4, written in cycle 4. Earlier, now it will be at 4 plus 4, 8. So, difference is 4. F. F was written at 5, cycle 5, read at cycle 5, written at cycle 7, 9L plus 7 when I am here. So, 7 will simply get delayed by 4, so it will become 11. So, difference earlier was only 2, now 2 plus 4 6, a very simple arithmetic. Then comes G, G was read by reader at cycle 6, 9L plus 6 as before, and G was to be written here. So, now 9L plus 4, 9L plus 5, 9L plus 6. So, 6 and again 6. So, difference now is 0. Earlier it was maximally negative minus 4, now it has become 0. So, I got rid of the negative thing. Similarly, the other ones, H was written at cycle 7 and was read at cycle 7, was to be written at cycle 5 here. That will get added with 4, so it becomes 9. So, 7 to 9, new difference is 2, and 8. I was read at I is read at 8. Earlier it was written at 8, now 8 plus 4 14, 12. So, difference earlier was 0, now 4. So, by introducing a delay between the two, I have got rid of the negativity here. Okay. I always got some positive or non-zero, positive or 0, there is some non-zero number of cycles by which each variable is to be stored in the system. All right. So, therefore, let us see the history. A, I am just rewriting from here. A is born in 0 and goes up to born in 0, and look at this T prime out 0 to 4. B born in 1 goes up to 7. C born in 2 goes up to 10. D born in 3 goes up to 5. E born in E born in 4 goes up to 8. F born in 5 goes up to 11. G born in 6 goes up to 6, born and dead in the same cycle. H born in 7 goes up to 9, and I 8 to 12. All right, but this is only one period. Lth, in the Lth input cycle, we read certain elements A, B, C, D up to I of the incoming matrix and had to store them by delay registers in the system over these cycles. But in the very next input cycle, that is L plus 1th, I will have another matrix. Maybe it will have elements A prime, B prime, C prime up to I prime. So, I have to store them also using the same delay register. So, there will be overlap, okay, as you have seen in the previous examples, and now I have to find out the minimum number of registers required. That is, I have to find out the maximum number of live variables in the system at any clock cycle. I need that many registers. If I have that many registers, then number of live variables at any cycle will be covered by them, I will be able to store them. Okay. So, that is done by lifetime chart. We all know how to carry out lifetime chart. So, we will simply obtain that from this figure. So, lifetime chart, you have to find out the minimum number of registers required, that is the magic figure. With that, you can store all the live variables, whether from the current cycle or coming from the previous cycle, previous input cycle, or belonging to current one. You can always store, that is whether there is overlap or not, you can always store all live variables in any particular system cycle by those registers. That comes because out of this lifetime chart. So, remember how we did the lifetime chart? There was a cycle, let us say regio 1, 2, 3, 4, 5, 6, 7, 8, 9. No point in going beyond, because I told you how to calculate by going back. We will do that again, so you will see. And now let us see the A, B, C, D, E, F, G, H, I. Okay. And number of this number of live variables. All right. Just for alignment, let me draw a dotted line. Cycle 1, cycle 2, cycle 3, cycle 4. Okay. Let's start with A. A is born in cycle 0. Just a minute. A is born in cycle 0 and goes up to 4. So, 0 to 4. Then B. B is born in cycle 1, goes up to 7. C is born in 2, goes up to 10. So, C born here goes up to 10. Oh, that means I need more lines, sorry. In fact, I need few more lines, sorry. Maximum here is 12. So, I need 10, 11, 12. You see this column 4, 7, 10, maximum is 12. So, I have to go up to cycle 12. Okay. So, I am dealing with C from 2 to 10. So, it goes down up to here. D is from 3 to 5. E from 4 to 8. F 5 to 11. G 6 to 6. So, G is born and date. H 7 to 9. 7 here goes to 9. I 8 to 12. Okay. Let us see here, people are just born, just a minute, A should start from here. So, in this cycle, I need 0, here I need 0, here 1, because B is born, but A is carrying on, so A is to be stored. Then here 1, 1, 2, this is just born, so 2, here 1, 1, 1, 3. This one is just born. Here 1, 1. Even in the cycle when it is consumed, it has to be stored in a flip-flop. It is taken from the output of a flip-flop. So, storage is required in that cycle. There is a 1 plus 1 plus 1 plus 1, 4. Not this, because this is just born. So, question of storing it does not come in this cycle. That comes from the next cycle onwards. So, just 4. Here 1, 2, 3, 4. This is just born. So, same question again. I will not count it. Just 4. 1, 2, 3, 4. Just born and date. So, just 4. Here again 1, 2, 3, 4. This not to be counted. This is just born. So, it is 3. 1, 2, 3, 4. This is 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 1. But period is 9. So, 0 to 8 and then this. So, as I told you, here 4 you have to go back by 9. If 9 you have to go back by the period 9 and pick up the figure from here, which is 0. That is, if I start actually say another cycle, there is a reader starts reading another matrix now in the L plus 1 cycle, input cycle, which begins from here. Then it would have been, there would have been another A, right, like this. So, that will get connected counted, that will get counted. That figure comes from this 0. Likewise, B would have come from here, and so on and so forth. So, I am considering that second input cycle L plus 1, but I do not really have to do all that phrase again. I can go back and pick up that figure from here. So, 4 plus 0, 0 is corresponding to this actually for A prime, okay, this may be B prime. So, 4 plus 0, all these were explained in the previous class. Then 3, you go back by 9, so it was 10, if you go back by 9 you have 1. So, 3 plus 1, this is 4, this is 4, 2, if you go back by 9, this is 11, so you have to go to 2, line 2, and here figure also 2. So, 2 plus 2, 4, and 1 which is in 12, if you go back by 9, you go to line 3, and this is 3. So, 1 plus 3, 4. So, 4, 4, 4, 4, 3, 4, 4, 4. So, you see maximum value is 4 here. That is, in any cycle, system cycle, maximum number of variables that are live bits which are required to be stored, which are not yet consumed, that is 4. Therefore, if I am giving 4 delay registers, okay, I can save them. Only thing is how to save them, which process, which technique to use, that is later. That is allocation, that is what I am coming to later. But theoretically, I know that with 4 registers in any cycle I can store for the next cycle. Okay. At any cycle, if you give me some live variables and you give me 4 registers, I can happily store them for use in the next cycle, and so on and so forth. Alright. If that be, how to use these 4 registers now to optimally carry out this saving, that is storage business. Okay, or not optimally, maybe efficiently carry out the storage business. A very popular technique is called forward backward data allocation, that I am coming to now. We have got the figure 4. So, now I am erasing it. Here, in the last example, we found out that minimum number of registers required is 4. In general, it can be say L, small l, or maybe say some other figure, maybe small m. Then what we do is this, we employ m number of m. If the minimum number of registers that comes out of that lifetime chart is m was 4 in the previous example, but in general suppose it is m. Then in this method, we employ m number of registers in cascade. You can call them R1 for register 1, R2 for register 2 and all that. Philosophy is this, data will continuously move through them, it will not remain static in any of them. But then input port or input terminal of every register is switched. That is, it can come from the previous register or it can come from elsewhere, maybe the output of some other register which is succeeding it. Okay. And output of every register also is switched. It can deliver it to the next register down the line or it can give it to some other place. So, both input and output will have switches. Okay. They are called switched input, switched output registers. And we have R1 for first one, then R2, the first 2, then R3, it will go up to Rm in that manner. So, it is a kind of cascade, though not necessarily that cascade connection has to be followed, like data from the output of any register may not have to pass to the very next one down the line, but it can just use the switch and go elsewhere, go to another register which is further away down the line. Okay. So, let us explain all this through this previous example where m was equal to 4. So, you will have 4 registers, combination is like this, R1, this is the cascade, R2, R3, R4. We will arrange them like this. This output is switched, it can move in various places. Input is switched, here input is switched, output is switched. Like this. Ordinarily, I would have had a cascade combination, but depending on the lifetime chart, I may have to move output of R1 to R3 rather than to R2 or to R4, or R4 output may have to be fed back to the R2 input, like that. That is how this connection, but will be formed. But remember, never data will be stored permanently in a particular register. Data will continue to move cycle after cycle from one register to another register. Data will not be static. This is the philosophy. To do this, what we do is this, we form a table, very nice table. The table looks like this. This is cycle input. Cycle means I am considering that Lth input cycle, which means system cycles are 9L plus 0, 9L plus 1 dot 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 up to 9L plus 8. I write R1 for register 1, R2 for register 2, R3 for register 3, R4 for register 4, and then output. Here also I will consider up to 12. So, cycle 0, 1, 2, 3, 4, sorry. Okay. We write in cycle 0, whoever is born. Here in every input, every system cycle only one fellow is born. So, I will carry out this example with that, but then there may be some cases where in a particular system cycle more than one fellow are born. Then what to do, that I will consider a little later after I complete this. So, in cycle 0 A is born, I write A. What we do, I write A here means I give A to the input of R1. If I write A here and then you see it goes from 0 to 4, right. It goes from 0 to 4. So, you remember that lifetime chart, it started from 0, then it goes to cycle 1, cycle 2, cycle 3, cycle 4, then gets consumed. So, A I give to R1 input in cycle 0 when it is born, and it is stored in R1 for that cycle and comes to R1 output. This R1 is stored, it is coming to R1 output at cycle 1. So, in this box means the output of the register is available. Then I give it to the input, I mean I do not disturb anything because it has to be stored till cycle 4. So, I give it to the input of R2, so the line continues. If it continues, it is given to the input of R2, it comes to the output of R2 at cycle 2. Then again it has to be stored in the next cycle. So, cycle 3 it continues, the line continues, it is stored in cycle 3 means R3 means it will be available at the end of the cycle here at the output of R3. But then I have to go up to 4. So, again the line will continue, it will be given to the input of R4, R4 will store at the end of cycle 4, it will come out here at the end output of R4. So, this is the beginning. A is given to the input of R1 because the line is hitting here. R1 stores it in cycle 1 and gives it its output, gives it at its output at cycle 1. Then again R1 output is fed to R2 input and R2 stores it and gives it at its output at cycle 2, and then R3 takes it at its input and gives it at its output at cycle 3. Then R4 again takes it and gives it at its output at cycle 4, and then it is over. So, we put a circle and we write here at this cycle I get an output A. Then comes B, B is born in cycle 1, so I give B here. So, you see there is no conflict. A is given to the input of R1 in cycle 0, then A moves to the output of R1 in cycle 1, that time I give B at the input of R1. Then in cycle 2, R2 stores A, R1 stores B. Then B is coming up at the output of R1 at the end of cycle 2, and at the end of cycle 2, A is coming up at the output of R2. So, at the output of R1 here, output of R2 here, there is no conflict. So, B continues in the same manner, then goes to the input of R2 because B has a long journey 1 to 7. So, B follows A. Okay. B is given to the input of R2, R2 shows it at the output here at the end of cycle 3, at the end of cycle 3 R3 output shows A. So, again no conflict. Then R3, as I told you earlier, this output goes to R4 input, R4 stores it in cycle 4, and in cycle 4 R3 stores it, it goes to the output of R3. Then it goes to R4, R4 had stored A in cycle 4, in cycle 5 it is free, so it is just happily taking it from R3, storing it, but I have to go beyond. Okay. 5, cycle 5 I have already reached the end of the journey, that is R4 output, but B has a longer path, I have to go to 7. What to do? Do not worry, I will for the time being stop here, but it is not the end of the journey. I know one thing, that this number of registers which is 4 is a magic figure, that is the minimum number of registers I worked out from the lifetime chart. That gives me an assurance that 4 is enough in any cycle to store the live variable. So, this variable is still live, but using this 4 I should be able to store them. That is, some register, if it is available at R4 output, okay, some register, one of them at least from R1, R2, R3, R4 will still be available to store it. I simply have to detect it, okay, one or more than one, I have to detect it or detect them and give it to the input of that. It will be available. That assurance comes from the figure that the number of registers, which is 4, is a magic figure obtained from lifetime chart. All right. So, I stop here, I do not end the journey, I will come back and take it to some register input for further storage, but quickly come to C. C is 2. So, 2 to 10. So, it goes like this. Again there is no conflict, as I told you, C is given to the input of R1 in cycle 2, but R1 output only cycle is showing B in cycle 2. So, no conflict. Then R1 stores C in cycle 1, in cycle 3 and gives it as output, and that goes to R2 input, R2 stores it in cycle 4 when it is free, then is given to R3 input in cycle 4, R3 has B at the output in cycle 4. So, input is free, so it is given to the input. So, in cycle 5 it is free, it is storing further, but C has a very long journey 2 to 10. So, again it is given to R4 input in cycle 5, that time R4 output was B. So, no conflict. Then the next cycle 5 R4 stores it, then again I have to halt here, I will come back, I will definitely find some register to store it in subsequent cycles, because the number is a magic figure which is enough for storing all the live variables in any particular cycle. Okay. Then comes D, D is 3 to 5. Okay. So, D, it is born, it goes like this, This is free, R1 input it gave, R1 output I have at 4. Then it comes here, it is giving to R2 input in cycle 4, cycle 5 when R2 is free, R2 stores it, gives it at the output, and it journey is from 3 to 5, so no need to proceed further. I put a round here and this is my D. All right. Then comes E, cycle 4 to 8. So, I again proceed in the same manner. Now, I think you can understand 4 to 8. So, sorry. This is E. F 5 to 11. Again I reach the end of the journey at cycle 9, but I will come back to this. Then G 6 to 6. So, G I do not have to store, it is born and dead. So, G here. Okay. After G I have got H 7 to 9. So, H born in 7, it goes like this. This is H, and I 8 to 12. 8. You all understand the meaning of this journey, by arrows. It goes up to here and here, 12. I. How to take care of these ones which got halted and have not been completed, this I will do in the next half of the lecture. Thank you very much.